So let us begin with the connection between non-relativistic Klein-Gordon theory and the non-relativistic harmonic oscillator and the Klein-Gordon theory. So non-relativistic harmonic oscillator and Klein-Gordon. So let me draw a line here somehow. Get space there. First of all, the harmonic oscillator action, the classical action, is given by half integral dt x dot square minus omega square x square. I'm setting m to 1, the mass of the particle to 1, and then after quantization, you arrive at a Hamiltonian H, which is given by half p hat square plus half omega square x hat square. It is also given by a dagger plus half h bar omega, where the relation between the x and p operator and a dagger operator are as follows: x hat t is root over h bar over 2 omega a hat e to the minus I omega t plus a hat dagger e to the plus I omega t, and p hat of t is equal to minus I root over of h bar omega over 2 a hat e to the minus I omega t minus a hat dagger e to the plus I omega t. For the Klein-Gordon field, the action is given by minus half integral d dx, d-dimensional, del mu phi plus m square phi square. So you see a relation here. So here the mu equal to 0, that is phi dot square, will have negative coefficient -1 coming from eta mu nu, and this -1, so it will be +1, so that is plus half phi dot square, which is same as which is analogous to plus half x dot square. Then you have minus divergence phi square, so that is del I phi. So minus half gradient phi square. So minus half gradient phi square minus m square phi square. So half times gradient phi square plus m square phi square is analogous to this, right? Omega square x square. Now you do quantization. After quantization, you come up with a Hamiltonian. So I'm giving the final formula. Of course, you have gone through the canonical quantization. So this is dnp omega p vector n hat p vector, where n is equal to d minus 1, which is equal to 3, the spatial part, and omega p is square root p vector square plus m square, and np is the number operator A P vector dagger A P vector. Number operator corresponding to P vector. And the relations between phi x and AP dagger, etc., are given by the following equations. So let me push this thing a little down to. So phi hat x is equal to integral dn p over 2 pi to the power n by 2 phi tilde vector p vector t to the I p dot x, where phi tilde p vector t is equal to phi tilde minus p vector t dagger. It's a real scalar field, so phi x is phi x dagger. If you do that, then that is how the Fourier transform phi tilde of pt will, that is the relation it will satisfy, and then you will have exactly the similar expression relation with this a hat p minus I omega pt plus a hat minus p dagger e to the power I omega pt. Now you see an analogy between this expression and this expression, except that this one does not have that p index, and it turns out that you will have p here and minus p here. This is also a convention to some extent. I will explain exactly where it makes a difference, and just a few more expressions. Let me write a few more expressions and then I'll explain. Then the momentum conjugate to this phi x is pi x equals integral dnp by 2 pi to the power n by 2. Phi tilde of p comma t to the I p dot x, where phi tilde p comma t satisfies similar reality condition p comma t dagger, and that has again the similar relation with the a and a dagger. So that means this x is analogous to this one, and p harmonic oscillator p is analogous to this one. I will explain why it is p and minus p here. And the canonical commutation relation is x hat p hat equals I h bar, and a dagger is equal to 1. And similarly here one has the equal time commutator T x by dy equals I h bar delta x minus y and AP AQ dagger is equal to delta P minus Q. So if one writes both to be P here, not P and minus A minus P as I have written, then the corresponding commutation relations will be P plus Q, delta P plus Q. It is because you want to, if you want to keep this P and Q to be same in order to have the non-trivial commutation relation, you have to have P and minus P. That is how, if you use, excuse me, if you use this and substitute, if you calculate this using this mode expansion, expansion and expansion in terms of AP dagger, and use this commutation relation, then only you reproduce this result, which is expected, which is what you want. If you write, you could write plus P here and here and here and here, and change the commutation relation to delta P plus Q, then you will get the right commutation relation. Now let's describe the Green's function. There you define delta t minus t prime to be equal to I vacuum expectation value time order product of x hat t and x hat t prime. We earlier calculated this expectation value of the same operator between an arbitrary final and initial state, and we already know the result. Well, we don't know the result. Okay, let me first write down the expressions and then I'll recall what was done before. Show that this is given by I theta t minus t prime d t minus t prime plus theta t prime minus t times d t prime minus t. Where d of delta t is equal to h bar by twice omega e to the power minus I omega delta t, and then also show that del t square plus omega square acting on delta t minus t prime is equal to h bar delta t minus t prime. This has already been done earlier because we considered the expectation value of this operator between an arbitrary final and initial state, and then we calculated how this operator acts on that matrix element, and we got this result with fi. So up to some factor of I, because there is a factor of I between delta and this matrix element. So for if you take f and I both to be vacuum, then this fi is equal to 1, and you get this result. But there is another way to show this, is that you expand x in terms of a and a dagger, and then calculate this matrix element and show that this result is right, where d of delta t is given by this, and then you directly apply this operator on this function, and taking into account that the time derivative will act on both this and this, and that time derivative of theta function is the Dirac delta function. So use that, and you can rederive the same result here. Okay, and correspondingly, for Klein-Gordon, you would define delta x minus y to be I times vacuum expectation value T of phi hat x, phi hat y, and then show that this is equal to I theta x minus y, theta x0 minus y0 times d x minus y plus theta y0 minus x0 d y minus x, where d x minus y is equal to d np by 2 pi to the power n 1 over 2 omega p to the ip dot x minus y. And then also show that minus del x square plus m square acting on delta x minus y is equal to h bar delta x minus y. This is exactly analogous to what we get in harmonic oscillator.